voltage dividers. Now we'll start with the first one, obviously. It says a circuit is set up as shown in the diagram. Calculate, A, the total resistance of the circuit, B, the current in the circuit, and C, the voltage across the 15 ohm resistor. To start with, part A, we use of course this is a series circuit, so for a series circuit we use this equation. RT is R1 plus R2, and of course the equations are covered in the video, the theory video I should say, on voltage divider, so if you haven't watched that, I would suggest that you do. After writing the equation, of course, we substitute the values. 7.0 plus 15 is, without the aid of a calculator, I know that is 22 ohms. And there we have it, that's part A. Part B, the current in the circuit. So I'm going to use V is equal to IR, that's Ohm's law. Now, the current is, of course, I, this is voltage, this is resistance. And in order to work out the current, I'm going to use the total voltage, that's the supply voltage of 9 volts, and the total resistance that I've just worked out, 22 ohms. And the other thing I'm going to do is to make this make I, current, the subject of the equation. I'm going to divide this right-hand side by R. So I'll get rid of the R there. There we go. I would also have to divide V by R as well, and that would give me I is equal to V divided by R. If you're not 100% sure about rearranging equations, believe it or not, I do have a video about that. Now, as I said, V is the total voltage, the supply voltage, divided that by the total resistance, and I should really have had the supply voltage written to 2 significant figures. Now you can see I've already entered this into the calculator, and the reason is because I'm going to write the final answer as 2 significant figures as well. I would imagine in an SQA exam it would be written to 2 significant figures at least. So there's the supply voltage, there's the total resistance. I'll write this number as 2 significant figures as well, and of course 0.409090991, that would, to 2 significant figures, be written as 0.41. So let's see, move that calculator, 0.41, and of course it's amps. Again, if you're not sure about rounding your final answer, there is a video about that. Part C. Now the voltage across the 15 ohm resistor. So we're going to call that top resistor, the 7 ohm resistor, we'll call that R1, and we'll call the 15 ohm resistor down at the bottom, we'll call that R2. So therefore the voltage that I want to find is the voltage across the bottom resistor, which I'm calling V2. And V2 is equal to the current times the resistance of the bottom resistor. So this is just Ohm's law again. V is IR. The voltage across the 7 ohm resistor, if I'm calling the 7 ohm resistor R1, that would be V1 is I times R1. But in this case, I'm wanting the voltage across the bottom resistor. I'm calling the bottom resistor in that voltage divider R2. So I want the voltage across it, I'm calling that V2. So V2 is I times R2. Remember, of course, this is a series circuit and the current in both of those resistors is the same. So we have 0.41 amps in the 7 ohm resistor, 0.41 amps in the 15 ohm resistor. Now let's see, that would be this current, 0.41, multiplied by, and it's the 15 ohm resistor, 15 is, so get rid of that, and I'm going to type this number here, 0.41 times 15. That gives me that, press the SD button, 6.15. Now again, I'm going to write that final answer as 2 significant figures, gives me 6.2 volts. There we go. Now if I was wanting that voltage across the 7 ohm resistor, it's not asking me for that. But because this is a voltage divider, the 9 volts is splitting obviously. We get 6.2 volts across the 15 ohm resistor, and the voltage across that 7 ohms would just be the supply voltage 9 minus, of course, what do we have? 6.2. So 9 minus 6.2 means that, of course, the voltage, press that SD button, it would be 2.8 volts across the 7 ohms. And as we said, the answer to this question, part C anyway, 6.2 volts across the 15 ohm resistor. In case you didn't know, the larger resistance gets the larger voltage across it. And of course, those 2 voltages, V1 and V2, have to add up to the supply voltage. So example number 2 says, a circuit is set up as shown in the diagram. Calculate A, the voltage across the 1K resistor, and B, calculate the voltage across the 4K resistor. So, of course, I could use that same method as I had before. When I work out the total resistance, I'll do this quickly, R1 plus R2. Now, a 1k resistor is 1 times 10 to the power of 3. A 4k resistor is 4 times 10 to the power of 3. Together, that would be 5 times 10 to the power of 3 ohms. Of course, that would be, I'll write this in brackets, of course, 5 times 10 to the power of 3 is 5,000 ohms. Now, remember what we did before as well was to work at the current, we used V equals IR. We then rearranged that equation to give us I as V over R. And, of course, what's the supply voltage? Supply voltage is 12. Total resistance is, I can either write 5,000 or I could write 5 times 10 to the power of 3. So, as I said, supply voltage over total resistance, exactly the same method as we used in the last question. Now, let's see, 12 divided by 5 times 10 to the power of 3 is this 2.4 times 10 to the minus 3. 2.4 times 10 to the minus 3. And of course, that's amps. And what do I want now? So I guess we're now wanting the voltage across the 1k resistor. So that would be just, if I call, as I said before, the top resistance R1, the voltage across it we'll call V1. And V1 is equal to the current times the resistance of R1, that resistance at the top of the voltage divider. That would give this current 2.4 times 10 to the negative 3 times, well, 1k is 1, I'll actually write it, 1.0 times 10 to the power of 3. That gives the following. So, get rid of that, 2.4 times 10 to the negative 3 times 1 times 10 to the power of 3. 12 over 5 is 2.4 volts. So 2.4 volts. Now, part B, I already know the current in both resistors is the same. So the current in the bottom resistance, that 4k resistor, would also be 2.4 times 10 to the minus 3 amps. So I could use V2 is I times R2. Current is 2.4 times 10 to the minus 3. And of course, the bottom resistance, 4.0 times 10 to the power of 3. Now, I'm sure you would have worked out that this voltage, of course, if the 12 volts splits and it's 2.4 volts across the top resistance, then the rest of the voltage must be across the 4k. So what would that be? It would be 12 minus 2.4 is that 9.6? I think it could be. But we'll just double check by working this out. So 2.4 times 10 to the power of, did we say negative 3, times, and it's the resistance, 4 times 10 to the power of 3, gives me this, 9.6 volts. So quite a lot of working, especially for part A, where we had to, for the voltage divider, work at the total resistance and the current. Current's the same for both resistors, of course. And then V1 is I times R1 or V2 is I times R2. I could have also used this equation. So I could have said that for part A, now this is based on an equation which is in the relationship sheet, which says V2 is equal to, and it's R2 over R1 plus R2, all in brackets, times Vs. Now, usually for a voltage divider, if it's drawn in this orientation, you could say, I would always call the top resistance R1, I'd call the bottom resistance R2, therefore the top voltage V1, the bottom voltage V2. And there is a reason why the equation is only written in this form. It's actually related to transistor switching circuits. So it only allows us to work at V2, the voltage across the bottom resistance. But of course you can change this from V2 to V1, but I also need to change that top resistance to R1. So it works out that V1 is equal to R1 over R1 plus R2 times Vs. As I said, this is not in the relationship sheet, but it's based on an equation which is, so what is R1? R1 is a 1000 ohm resistor. Now, previously I wrote these resistances, 1k is 1 times 10 to the power of 3 and 4k is 4 times 10 to the power of 3. I'm actually going to write the 1k, just to remind you, 1k is 1000. So that's R1. R1 plus R2 is of course 1k plus 4k, well, that's 1000 plus 4000 is 5000, that's in brackets, multiplied by supply voltage is 12. So let's see, in brackets I'll say 1000 divided by 5,000. I know what you're thinking, he's not using the fraction button. Anyway, that gives us 2.4 volts. So that's a lot quicker than the method we used before. And of course, it's a method that can be used if we're only working out the voltage. If we want the current, I would suggest obviously memorising that first method. For part B, to work out the voltage across the bottom resistance, that's of course V2 is equal to R2 over R1 plus R2 times Vs. And of course that is 4,000 divided by 5,000 times 12. And I know this of course is going to be what we worked out before. Why don't I just change this sum? Delete that, make that 4,000. So 4,000 over 5,000 times 12, as I have here. So R2 over R1 plus R2 times Vs. That's going to give us V2. And I'm sure we know, press equals, and then of course press the SD button. It gives us 9.6 volts, as we had before. So that is, believe it or not, example number 2. Is there another example? There is indeed. Now, I wonder if we're using the same method. So what does it say? A circuit is set up as shown in the diagram. Voltmeter V1 registers a voltage of 2.4 volts. Calculate voltage V2. Determine the supply voltage of the circuit. And that's for part B. So we'll get rid of this piece of paper, move that over there. Now, we're actually using a slightly different equation. And again, this is mentioned in the actual video which goes through the theory of voltage dividers. So for part A, we're going to use V1 over V2 is equal to R1 over R2. So the ratio of voltages is equal to the ratio of resistances. So let's see, we have at the top of that voltage divider V1, at the bottom V2. That means the top resistor, we're calling the 12 ohm resistor, we're calling that R1. We're calling the 33 ohm resistor R2. Now, to calculate V2, I guess the first thing we should do, we know the other three values, we should substitute those into the equation. So we know, as it says there, that voltmeter V1 registers 2.4 volts. So we've got 2.4 over, well, we're trying to find V2. We don't know it, so we just write V2. And that's equal to R1 over R2. So R1, we said, is at the top of the voltage divider. R2, that's the 33 ohms. Now, what we should be using at this stage is cross multiplication. And I'm going to start with bottom left times top right, because I want that V2 to be the subject of the equation. So I know that V2 multiplied by 12, if I'm just multiplying this times that, that will also be equal to 2.4 multiplied by 33. Okay, now let's write that down. So V2 times 12, I'll write it here, V2 times 12 is equal to, so that was this diagonal, 2.4 times 33. 2.4 times 33. Now at this stage, what I could do is I could work out 2.4 times 33. I'm not going to, I'm going to actually keep that in brackets. What I'll do, just to get V2 on its own, I'll divide that side by 12. Just to give V2 on its own. That means I need to divide all of this by 12. So of course that gives V2 is equal to, so I've already divided the left hand side by 12 to give V2 on its own. I need to divide all of this by 12. So that's going to be 2.4 times 33 divided by 12. That will be V2. Find the calculator again. Get rid of that. So in brackets, 2.4 times 33 divided by 12. Whoops, that's not 12, that's 22. So change that number there. That gives me 33 over 5. Press SD, it gives me 6.6 volts. There we have it. So 6.6 volts. So that's part A. Part B is not going to be difficult at all, because I know, of course, that this is a series circuit, and the whole point with series circuits is that voltage splits up. It's a voltage divider question, after all. So I know that Vs is just going to be equal to the value of V1 plus V2. V1 is in the question, that's 2.4, and this is V2, 6.6. Let's see, 6, okay, I know that answer, but I'm going to work it out in the calculator anyway. 2.4 plus 6.6. Now, I would still suggest using your calculator, even though you think you know the answer, just to double check. I've seen lots of pupils try to work out an answer in their head because it seems like a fairly easy question, but make a mistake. So I knew the answer to that. I knew it was going to be 9. I'm going to write it to two significant figures, 9.0 volts. Just use your calculator. If you have one, be as well use it, even though you think you know what the answer is. So there we have it. So basically, first two questions we used a certain, in fact I've shown you two different equations. That third question we used a completely different equation. Let's see the next one. So voltage divider number 4. Now that's a strange circuit there because we've got not just a 5 ohm resistor there on the right hand side, we also have some parallel branch. So it says a pupil builds an electric circuit as shown in the diagram. Calculate the values displayed on the ammeter and the voltmeter. Now, I guess the first thing to do is to work at that current. And if you remember the first two examples, the current depended on the total resistance of the circuit. So I guess that's the first thing I'll do. I'll work at the total resistance of the circuit. And let's see, I'll write A here. Now, in order to work at the total resistance of the circuit, what I'm going to do is I'm going to work at the resistance of that parallel branch first. And then, because we have 5 ohms in series with that, I'll then add 5 ohms to that value. So we've got two 20s in parallel. Now, I know already two 20s in parallel, the effective resistance will be 10 ohms. But if you don't know that, obviously you need to work it out. Let's see, and obviously if this is a show question as well, I should also be using the correct equation. So two 20 ohm resistors in parallel, 1 over RT is equal to 1 over R1 plus 1 over R2 is equal to, so 20 or 1 over 20 plus 1 over 20. And this is the point where I want to use my fraction button. So let's see, 1 over 20 plus, I don't often use the fraction button. I think when I was younger, calculators didn't have fraction buttons. Don't know. That's my excuse. Anyway, you saw there, that gives me 1 over 10. 1 over 10. Now, that is 1 over RT. So if 1 over RT is 1 over 10, what I want to do is I want to flip this side upside down. So from 1 over RT, if I flip that upside down, it gives me RT over 1, which is actually just RT. I then flip this side upside down. So 1 over 10 flipped upside down goes to 10 over 1, which is just 10. There we have it. So the total resistance, or the effective resistance, I could say, effective resistance just of the two 20 ohm resistors in parallel is 10 ohms. So total resistance in the circuit, all right, total resistance in the whole circuit is of course that 10 ohms for the parallel branch plus the 5 is 15 ohms. Now we've got that, we've got the total resistance in the circuit. We also have the total voltage in the circuit that's going to split. That's the 9.0 volts. So what we could do at this stage is, of course, moving this up, use Ohm's law. This is much like, from this stage, much like the first two examples. So V is equal to IR. And again, I'm going to rearrange that equation. So I want the I, so I want to divide the right hand side by R, just to give me the I on its own. I then have to divide the left hand side, V, by R as well. So it gives me I is V divided by R. So therefore I is V over R is equal to, supply voltage we said was 9.0 divided by the resistance of 15. And that gives, so 9 over 15. What is 9 over 15? Type it into the calculator. Oh, I thought it was going to say 9 over 15, but no, simplified it to 3 over 5, press the SD button again, it gives me 0.6 amps. So far we know that that ammeter is going to display 0.6 amps. Of course, it's the same current. Usually, if we just have two resistors, the same current all the way around the circuit. So basically in the 5 ohm resistors, or resistor, I have 0.6 amps. Those two 20 ohm resistances, the current shared between those two resistors would be 0.6. In actuality, each one of those would get 0.3 amps. And then, of course, those two currents would basically merge together after the resistances. If I was to measure the current, say, on the left-hand side of the circuit, it would also be 0.6 amps at that point. Certainly the current on the right-hand side of the circuit, where the ammeter's drawn, would be 0.6 amps. So, now we know the current. We know, as we said, that the current in that 5 ohm resistor would be 0.6 amps. We also know its resistance. So let's say that we call, in fact, I don't know why I wrote A. This isn't part A. But if you're understanding this so far, we've got the current. To work out that voltage, let's say that the effective resistance of the two parallel resistances, or resistors, we'll call the resistance or effective resistance of those two, we'll call that R1. We'll say the voltage across that parallel branch, we'll call it V1. So therefore we're going to call the 5 ohm resistor, we'll call that R2, and therefore the voltage that we're trying to work out, you can see there's only one voltmeter in the circuit, we'll call that V2. So we'll say that we're trying to work out V2, and that's equal to the current in the circuit, which we know is 0.6 amps, times the resistance R2, which we're saying is the resistance on the right, the 5 ohm resistor. So that gives us 0.6 times, what does it say there, 5.0. Again, I know what this is. I can work it out just in my head, but just type it in anyway. It's not going to take too long, just in case we make a mistake. It works out as 3. I'm going to write that. Two significant figures gives me 3.0, and of course it's volts.